and then 6 9s are 4, 6 5s.
Shift it one more. That 4 should be one more to the left.
And 6 5s are 0. We add them up, and we get 4.
17.
It's a 7.
4 1 7, which is 4 1 7. No, it's commutative. I mean, you can model this actually by polynomials. And we did. But the point I wanted to make was that this, because it's well known that penal colonies have very good dental care, and so there are no caries on the island. And just as we were writing that, there was a cartoon in the New Yorker that said, I'm just here for the dental. So we got permission and included that to illustrate the argument. But what we were interested in is what are the carryless primes? And we went through it. And, we worked out, what are the carryless primes? Is 11 a prime? No, because 9 times 99 is 11. Well, all right. So if you do that, there are no primes. So what you have to observe is that you have not just 1 as 1, the multiplicative unit is not just 1, but 3 times 7 is also 1. So 3 and 7 and 9 are also multiplicative units. So there are 4 multiplicative units. And then you can say, all right, P is a prime if its only factorization is as P times one of the units times a conjugate of P. So the carryless primes are 21, 23, and so on. And it's tricky because you have to worry. If you multiply 4 times 5 0 0 5 5 5 5 5 0 3, you get 2. So it's a little bit. So that's not really what I want to mention. There was a sequence from Remy Seacrest. I was going to do it on the board, but I think maybe it's clearer here. Okay, so you write down numbers. It's a sequence defined in the following way. A of n, it's the smallest number you haven't seen before, such that when you add up all the terms up through A of n, there are no carries in normal arithmetic. Right? So you start off, the smallest number we haven't seen before is 1, right? You haven't seen me write down any numbers before. So the first number is 1. Now we write, what's the smallest number we can write down such in base 10, such that there are no carries? Well, I can write down a 2, because the partial sums are 1 and 3, and so far no carries. Now I can write down a 3, greedy, no repeats, no carries. So 1 plus 2 plus 3 is 6, we're good. Can I write down a 4 here? No, because we get 10 and will be a carry. All right, 5, no. 6, no. We have to go up to 10. And so 10 is the next legal term, and the running sum is 16, and there are no carries. So you can do it. Here's the 10. The running sum is 16. Then we can do 11, and we get 27. 12, we get 29. And because we've reached a 9 in the ones column, we can no longer have any, in this column, it must be zeros from then on. Otherwise we'd have a carry. But in the second column, the tens digit, we can put down 20, we go from 39 to 59, and then 30 up to 89, and now we're stuck, we have to go up to 100, get 189, and so on. You do this, and after this many steps, this column is full. We've got a 9 here, so I did a horizontal line here to indicate we can't put anything else in this column. So the first 2 columns are now saturated. And then we keep going. And you find that after 17 steps, all the first 4 columns are full up, saturated, but we can start again in the 5th column, and what we get is a recurrence of period 17. And the recurrence then is that if we go down 17 steps, we add 4 zeros. And that happens starting at the beginning. So we have the recurrence of order 17 that says that A of k plus 17 is a of k times 10 to the fourth. And it begins right away at the beginning for all k greater than 0. So now you can generalize that to any base. So that's why I wrote 10 here. And if you do it, so here's base 9. Base 9, same thing happens, but it's got a different period. The recurrences of order 4 instead of 17. And it doesn't begin until the fourth step. So the recurrence here is that a of k plus 4 is a of k times 9 to the power 1. We add every 4 steps, we get an extra 0 at the end. So it's periodic. I mean, it's a recurrence of order 4. And so now what about base B? And here's the interesting question. He conjectures that whatever base you pick, the same thing happens. For any base, there is a recurrence of order, some order D, and D is given by this first column. It starts at the k north step, so for base 10 it began at step 0, for base 9 we had to go to step 3 before it started, and the power of the base that we multiply by, well, it was 4 in base 10 and it was 1 in base 9. So there are 3 sequences there. The conjecture is this always happens.
Yeah, I believe that.
Can you prove it? Yeah, you probably can.
Yeah, but do I want to?
Yes, please. Yes.
What's d divided by n? Looks like it would be kind of. That would be
Yeah, there's some if you plot these sequences against each other, they look pretty wild. This is just the order of the recurrence as a function of the base, from base 2 up to base 10,000. That's a very weird graph. What's going on here? So this is greedy, carryless sequences in base B. Remy sequenced, very interesting. There was another sequence that somebody, I think this was John Schoenfield, JES, one of the best editors-in-chief we had. Very thorough, very conscientious. And he pointed to this old sequence. This was December 25th of last year. He said sequence 141436 is a total mess. And I said, yes, I agree. I'll edit it. And when I edited it, it came out looking pretty nice. So and I invented a name for this. The sequence was sent in by a guy called Tisdale. So I call it the Tisdale sieve. And let P be the primes, let N be the non-primes. And we define an infinite set of sequences, disjoint sequences, in the following way. The first term in the ith sequence is the smallest number we've never seen before. And then once we get started with Si of 1, let me do it. The first sequence, we haven't seen 1 before, right? Same one that we didn't see before over there. We haven't seen it here. So this is a non-prime. So the rule is, you look for the first prime. We must have alternating primes and non-primes. We start with 1, and the next term is the 1th prime, which is 2. We now look for the second non-prime, which is 4. And then the next term is the 4th prime, which is 7. And then the 7th non-prime, which is 12. 7th non-prime is 12. And then the 12th prime is 37, and so on. So S1, starting with 1, primes and non-primes alternate, according to the rule. Now, the next sequence, we look for the first number we haven't seen before, which is 3. We've got a 1 and a 2, we don't have a 3, so we begin with 3. 3 is a prime, so the next term is the 3rd non-prime, which is 6. The next term is the 6th prime, which is 13, and so on. We fill out that whole row, then the first missing number is 5, and we repeat. The sequence is the sequence of the first terms. And there was a conjecture by Richard Matter that this is the union, this sequence is the union of two sets. It's the union of P, primes with prime subscripts, and n of n, non-primes with non-prime subscripts. So, at Bell Labs, in the older days, AT&T Labs, later, at the end of the afternoon, I would often wander down the corridor and look for an open door and say, look, do you want to see a really nice sequence that came in today? Well, I can't do that anymore, although I'm doing it here partly. But I did send email to my former colleague, David Applegate, because we were discussing something else, and I said, look, if you had been down the corridor as you used to be, I would have stopped by and shown you this lovely sequence, which I haven't worked on at all, but there's a conjecture. The conjecture is that this is this. And he found a very nice proof. So he proved the conjecture, and what's more, he gave a nice lemma that explains what's going on. So his lemma says, if you're given a function f, mapping integers to positive integers to positive integers, which has the property that f of n is bigger than n. It's an increasing function. And define a set of sequences in the way I just did. So the rule is, the first term of the ith sequence is the smallest number we haven't seen so far. And every other term is you apply f to the previous term. And if you do that, his lemma tells us what the leading terms are in this set of sequences. And the answer is, it's the values of n that are not in the image of the function. And the proof is half a dozen lines. Elementary argument, very nice proof.
So it's much more general, that's why
Yes,
it's much easier.
yes, exactly. So, and now you apply the lemma. The f we want is that it's, if k is a non-prime, we take the f of k as p of k, if k is a non-prime, f of k is n of k if k is a prime. And the conjecture follows. Yeah, square permutations. So, this was something I wanted to have a chance to do show you my shuffle. So you, there are square permutations and square binary words. So my friend Percy can do a perfect shuffle. I can do a perfect imperfect shuffle. So here's an imperfect shuffle. You take two decks. I mean, you cut the deck in half, and you do this. And that's a shuffle. The shuffle is technically that everything from one half has to come before everything else. I mean, you've got to interleave them in the obvious way. They don't have to be interleaved properly, they just have to be interleaved. So that's the operation that I wrote it here using Yama. I meant to write Sha, but I'm so used to writing Yama that I did it with the Japanese thing. But they should be three equal. So anyway, let me explain this one. This is an old sequence 191755. The new one was from December 15th, but I don't understand that quite as clearly. The old one are square binary words. You take, how many binary words of length 2n are there, which are shuffles of a binary word with itself? So for instance, binary words of length 2, we can have 0, 0, 0, 1, 1, 0, 1. If we take 0, 1 and we want to shuffle it with itself, so 0, 1, 0, 1, shuffled with 0, 1, it could be 0, 1, 0, 1, or it could be 0, 0, 1, 1. And I think that's all it could be, right? So there are two possibilities, depending on how good you are at shuffling. So here there are two, and here there's only one. 0, 0, 0, 0, and here there's the complement, and here there's 1, 1, 1, 1. So we have we have 6. So that's this 6 here. That's the number of square binary words. A binary word shuffled with itself in all possible ways. You, shall, you, thee shall thee. How many are there? And the answer is, it's sequence 191755. We know 15 terms, and there's no theory as far as I know, no formulas. It looks like a nice combinatorial question. Ah, yes. Yeah. Very easy question. I probably will skip this. I've spent a lot of time in the past 2 weeks. This is, I'll just tell you, I'll skip that. There are lovely sequences, and
You're going to post the slides in your homepage? You're going to post the slides in your web?
Yeah, I guess. Yes. Yes. Yeah, and I can prove 280866 is a permutation of the natural numbers. And now this came in just the other day, sequence 28. You know, we have 2 keywords that are worth looking out for. If you see the keyword look, it means look at the graph. You'll see something interesting. And if the keyword is here, listen to it. So here's, 281488. It was sent in by Andrei Zabolotsky. And the definition is, A of n is the sum of certain previous terms. It's the sum of A of d as n goes from 1 to n minus. As d goes from 1 to n minus 1, and d has to divide n minus 2, and you begin with 1, and you get that sequence. And so this is the here, and this is the look. Here are the graphs. 200 terms, 20,000 terms. And because it's got negative values, we do it in 2 different ways. Log of the absolute value or the inverse hyperbolic sine, which actually is more mathematically appropriate. Right. And then we have, so this is, so Michael Nivon is a musician in Copenhagen, and he offered to help with the OEIS. And I said, we have lots of illustrations, figures illustrating sequences, but we have very few musical pieces based on sequences. So he sent in 2 pieces. This is the surreal cantata. He said, be careful, there are some very low notes. It'll sound like, if you've got a good musical system, it'll sound like there's an earthquake coming. This one is much, much worse. So I'm just going to play this, but already you can hear. So if you like this kind of thing, please become a volunteer editor. There are no requirements, there's no pay, but it's fun. Send me an email if you want to help. So, I'll stop there.
Thank you very much. Concept. And you have to get to answer questions later.